Hello everyone, welcome back again for the discussion of this, continuing the same discussion with Unit 2. So as of now, you know about that course introduction and after that Unit 1, and now we are moving to that the matrices and calculus is our course title in Unit 2. So here in Unit 2, already I explained that eigenvalues, eigenvectors. So here we are focusing especially the quadratic forms. We can see that now, take class. Quadratic forms. What is the quadratic form defines? What it tells about that. An expression of the form q is equals to x transpose ax equals to summation of I equals to 1 running to n and summation of j equals to 1 running to n aij xj where aij are constants is called quadratic form of n variables with x1 x2 a dash xn variables. If the constants aij's are real numbers, it is called real quadratic form. And this is the example I kept that using two variables x and y. 3x square plus 5xy minus 2y square is a quadratic form in two variables x and y. 2x square plus 3y square minus 4z square plus 2xy minus 3yz plus 5zx is a quadratic form in three variables x, y, z. And here every real quadratic form in n variables can be expressed in that form x transpose bx, where x is equals to x1 x2 dash dash xn whole transpose and column matrix is b. Column matrix is b and real symmetric matrix of order n. Next, containing that quadratic form corresponding to real symmetric matrix. And here we can see that we have taken that one matrix be a real symmetric matrix and x is equals to vectors, be a common matrix of that thing, and then we are representing the x transpose ax in the form of summation of I2 to n, j1 to n and ai j, xi, xj, and can be getting into that. This is the form, right? After multiplying that, a11 x1 square plus a22 x2 square plus a33 x3 square plus 2a12 x1 x2 plus 2a13 x1 x3 plus 2a23 x2 x3. And this x transpose will be like this, and this is aij and this is x, where a1 to a21 are same, a13 a31 are same, a23 a32 are same. X transpose ax, where a is a symmetric matrix quadratic form, see more variables can similarly be written in the form of x transpose ax by suitably defining that a. Next, quadratic forms. So few of the examples I picked up because to understand that very easily. Write the matrix reducing into the quadratic form ax square plus 2hxy plus by square. The given quadratic form can be written as ax square plus 2hxy plus by square can be written in the form of x transpose ax like this, xy, and a is a ah, hb, and then xy, right? And this is the matrix we got it. So this is the matrix we got it. And next, find the symmetric matrix to that quadratic form x1 square plus 2x2 square plus 4x2 x3 plus 3 plus x3 x4. So we need to write in the form of x aij and then x transpose aij and then x. So we are going to write by using that this is the matrix we are going to get, because here the variables involved here x1 x2 x3 x4, four variables are there. So that's the reason you are going to get that 4 by 4 matrix. Next, find the quadratic form relating to the symmetric matrix. See, you are writing that in a reverse mode. So now the matrix is given. Now you are going to write that the quadratic form. So the quadratic form is related to x transpose ax. No, now we are multiplying that x transpose we need to write, and then a whatever the given data you are writing, x also we are writing. After that we are going to get that x square plus y square plus z square plus 4xy plus 6xz plus 6yz is the final quadratic form for the given matrix. Next, canonical form, also known as normal form of a quadratic form. So how it defines that? Let x transpose x be a quadratic form in n variables, then there exists a real non-singular linear transform x is equals to py, which transform x transpose ax to that y transpose py. That means these variables transform to y. Okay. So what is the form here? What is the form? So that form is lambda 1 y1 square plus lambda 2 y2 square plus lambda n yn square. So under the transformation, we can call it as this x is equals to py, right? E is called canonical form of that X transpose AX, where B is equals to diagonal lambda 1, lambda 2, dash dash lambda n. And then here, what are the nature of the quadratic form? You are going to discuss briefly here. Index of a quadratic form. The number of positive terms, that means number of positive terms. What are the positive terms will be there? No. So the number of positive terms in a normal form of a quadratic form is called the index of the quadratic form. It is denoted by P. Next, signature of the quadratic form. Signature of the quadratic form is defined as the differences between the number of positive terms and the number of negative terms in its canonical form, and is denoted by S, where S is equals to P minus, that means index minus R minus P. We can get the 2P minus R, where P is index, R is a rank, you know very well. Now, finally, rank of a quadratic form, how you are going to define. The number of non-zero terms in canonical form of a quadratic form function or form is called that the rank of the quadratic function, and it is denoted with that R. Next, so simple ma, very simple, only the form, not like this descriptive manner. Index of a real quadratic form is nothing but P is equals to number of positive eigenvalues, shortcut ma. Then signature of a quadratic form is nothing but S is equals to positive minus negative eigenvalues. Rank of quadratic form is nothing but the number of non-zero terms in a canonical form of a quadratic function is called that the rank of the quadratic function, and it is represented by R. Next, by using eigenvalues, here I need to show that in this slide. I need to explain. Nature of quadratic form by using eigenvalues. It's very easy. The quadratic form can be defined like positive definite, negative definite, positive semi-definite, negative semi-definite, indefinite, right? All the eigenvalues are positive. Yes, it is positive definite. All the eigenvalues are negative, which is a negative definite. If all the eigenvalues positive and then 1 0 is there, positive semi-definite. All the eigenvalues are negative, if at least 1 0 will be there, yes, negative semi-definite. If both will be there, positive and negative, we can call it as a indefinite. So hope you understood that this. Next, quadratic forms in another method. This may not be using, but I can tell you that using principal minus method. So this is the quadratic form, no, and from that we are going to get that matrix, no. After that, see, this is called D1, only single, and sorry, AH and HB will be there. This is called D2, and whole thing will be the D3. By using D1, D2, D3, we can D1, D2, D3 all greater than 0, positive definite. Next, D1, D3 will be negative and D2 is positive, then we can get known as negative definite. Positive semi-definite, D1, D2, D3 greater than or equals to 0. Maybe a number of zeros also will be there. Negative semi-definite, D1, D3 is a negative pakka and D2 is positive, at least 1 0. Then we can say that this negative semi-definite. Indefinite means greater than 0 will be there and greater than value and less than zeros will be there in that. So this is little bit tough than this. This is very easy. You decide that whatever you want, which method you are comfortable. Next, identify the index and signature of the nature of the quadratic form. This is the quadratic form they have given. We need to identify that now. What is the form? Now, by data, the given equation will be, you have written from the data, you are going to write that A, and then you are writing that characteristic equation. Why you are writing the characteristic equation? Because you need to find out that the eigenvalues. That's the main thing, no? So, what is the characteristic equation? You know very well, A minus lambda I is equals to 0. From that, you are going to get that the lambda values are 1, 2, 3. So, all are positive, no? All are positive. According to that, which is a positive definite, and all are positive, index is 3, and the signature will be 2p minus r. So from that, 3. So like this. The second method I am not going to tell, right? Similar way we can work out with that second example. Third example. Hey, I need to tell about that. Here 0 will be there, no? So that's the reason positive definite, because all are positive except, at least 1 0. So positive definite. 2 zeros and 6 is the positive. Yes, positive definite. Semi-definite. All are negative. Yes, negative definite. And one is positive, one is negative. That is indefinite. So we can do that, those problems, right? Next, reduction to normal form by orthogonal transformation. Definition of orthogonal matrix. Yeah, already we discussed now. Orthogonal matrix is nothing but A transpose E equals to A transpose equals to I. And that this transformation will be there. No? So that's the reason X is equals to Py. So if the transformation X is equals to Py and P is orthogonal matrix, then quadratic form Q transposed into that canonical form C, then which is known as the orthogonal transformation or reduction of QF to CF. Next, ma. So this is the note. Already we discussed the same thing. All lambda values corresponding eigenvectors will get it. Pairwise orthogonal is pakka x1, x2, x2, x3, x1, x3 pakka you have to show that 0. All eigenvalues will get that eigenvectors are linearly independent. Otherwise, you are not going to get that this reduction. Even E2, E3 all are normalized vectors. Then we can say that lambda 1, lambda 2, lambda 3 are pairwise orthogonal. If A is nth order square real symmetric matrix, the above results can be generalized. And A is of order n, and it is not possible to have n linear independent pairwise orthogonal eigenvectors. The above procedure does not work. So the last statement you should be very careful with that. And procedure, first quadratic form you are writing, finding eigenvalues, finding eigenvectors along with that normalized vectors, and you need to show that pairwise orthogonal and find that P and then find the D. After that reduced into C is equals to Y transpose dy and write this form, and then find out that linear transformation X is equals to Py. Note that always pairwise orthogonal should be applicable, otherwise this problem is not going to get that to applicable with that, right? So it's mandatory x1 x2 x2 x3 x1 x3 equals to 0. So this is the problem. They have given that the problem. First, what you are doing, writing into the matrix, finding the characteristic equation, because you have to find out the these eigenvalues, sorry, and 2, 3 are the eigenvalues. Now you are going corresponding eigenvalue vectors you have got. After that you are writing D and finding pakka you are checking that this is a pairwise orthogonal, and the normalized vector you got, diagonalization you got, right? And finally you are going to write that C is equals to or Q is equals to Y transpose D and then Y. This is the canonical form. Similarly, you can continue with that. This is the second problem. You can do the homework. So thank you once again, and we'll see that in a